This is joint work with all these people. Okay, so I want to speak about how to verify relational properties. So these are kind of properties that they refer to two runs of two programs, right? So the simplest example is probably equivalence. So you have on the input of the two programs, two inputs related by equivalence, and then on the output, you also have outputs related by equivalence. Right, and this can also be specialized to the case of two runs of the same programs. So in this case, we can speak, for instance, about non-interference, and we can say that if the inputs of the two runs of the program are equivalent at the low security level, then the outputs should also be equivalent at the low security level. Right, so well, at least in the higher order setting, this is solved. One of the possible solutions is using relational refinement types. So I assume most of you are familiar with refinement types, but just in case, so these are types that are qualified by some kind of logical predicate. So for instance, we can speak about even numbers as a refinement of the natural numbers. We would say that T has the type of even numbers, and the type of even numbers are the excess in NAT, such that they are twice some other NAT. Right, so this can be generalized to what's called relational refinement types. And general refinement types, they can be interpreted as a kind of subset of the whole type, but relational refinement types are interpreted as a relation over the type. So in this case, I'm representing the equality relation in the natural numbers, and that judgment would mean that T1 and T2 are equal natural numbers. Okay, so this approach, it has a very good properties. So the first of all is that it's very intuitive. So you can, for instance, type monotonic functions, saying that it's the type that goes from the less than relation to the less than relation. They are syntax directed, meaning that you know which rule to apply just by looking at the top connective of the terms you are relating. And they are very good at exploiting structural similarities, right? So if we have, for instance, two programs you are relating, and we have on the left-hand side, if B, then twice x, else x plus 1. On the right-hand side, we have if B, then twice x, else x minus 1. Then ideally, we would like to only consider the differences, right? Because the rest of the program is the same. So we only have to consider the else branch and see how this affects to the meaning of the program. And of course, since there are a lot of theoretical and practical developments for refinement types, then potentially this could be reduced. But they have some limitations. So suppose we want to prove that these two functions are, well, these two terms are equal, right? So the first term is the take function applied to map of some list, and the second term is the map function applied to take of some list. So these two should be equal, right? Because it doesn't matter if you map a function over a list and then take the first n elements than if you do it the other way around. And we would like to give it, for instance, that kind of relational refinement type. So these are two lists, and they're related by equality. But what happens? Well, you start applying the typing rules, and at some point you would have to type something like this, take with map, and then you realize that these two functions don't have the same type, because take takes a natural number, and map takes a function. So this is the start point of our work. So what were our goals, and what do I want to convince you that we achieved? So we want to have a foundational system to prove relational properties, right? And this is appropriate to this session, which is foundation of higher order programs. We want to keep syntax directedness. We like this because we think that it's the best way to reason about relations. But we don't have to be restricted by the types. We want to be able to type to relate terms with different types and with different structures as well. So to achieve this expressiveness and foundation of our system, we have the HOL as a base logic. And people talk about HOL when people talk about HOL, they mean different things, so I will specify. So we have lambda terms over simple and some inductive types, such as NAT, list, and so on. We have axiomatically defined predicates over these terms. So for instance, you can define the prefix predicate saying an empty list is a prefix of L of any list. And if T is a prefix of L, then you add the same element to both and there are still prefixes. And then you combine this using propositional connectives and quantification over these simple and inductive types, but not over predicates. So you might be asking yourselves, well, why not I just prove relational properties in this directly? And the reason is, well, two reasons. So we lose the syntax directness, and this doesn't let you do structural reasoning, right? You want to reason about the similarities of the program as well as possible. And here you would just, well, you will lose that. So instead what we are doing is we are going to build a system to prove relational properties over this logic. And by the way, although it's not in this paper, we've also done it for slightly different logics, this same approach. So first we have our HOL judgment. So we have some context containing term variables. We have an assertion context over these term variables, and then we have a predicate that we prove. Over this, we build what we call Janary HOL, or UHOL for short. So we have the same context and the same assertions, and then we have a distinguished term that we type, and for which we prove some property phi. And we use the variable r to represent the term we are typing. And in the same way, we can build what we call relational HOL. So we have two terms that we type, and then a property phi that relates them both, and we use these variables r1 and r2 to represent these terms. And by the way, I forgot to say this, but throughout all the talk, we are going to use the subindex 1 to represent the term on the left of the relation, and the subindex 2 to represent the term on the right. Okay, so this might look similar to refinement types, but there's a key difference, which is that there's a separation of concerns between types and assertions. So in the generic case, this does not matter that much, but in the relational case, you see that the formula is actually part of the type in some way, but in our system, the formula is separate of the type. So you can, you are at the same time deriving a typing judgment and a logical formula, but they're not, so the logical formula is not part of the type itself. And this lets us define two kind of rules. So what we call two-sided rules, they relate two terms that have the same type former. So for instance, two lambdas. And one-sided rules, they relate two terms that have a different term format at the top. So you can relate, for instance, a lambda with an application. And then you have a rule that introduces the lambda on the left, or a rule that introduces the application on the right. So I'm going to give more concrete examples of these rules. I will walk you through this, so you don't have to read it the whole. So first, we have in red a typing judgment, two typing judgments. So we have, we introduce two lambdas. We abstract over the variables lambda x1 and x2. And at the same time, we have a logical judgment. So what this logical judgment is saying is very intuitive. You just say that, well, if from the premise that x1 and x2 are related by phi prime, you can conclude that t1 and t2 are related by phi. Then you can see lambda x1 t1 and lambda x t2 as two functions with the precondition phi prime and the postcondition phi. And in this case, the pre and the post condition are relations instead of being usual predicates. And we put these two parts together and we get our abstraction rule. The application rule is dual. So you just say that T1 and T2 are two functions with the precondition phi prime and the postcondition phi. And then U1 and U2 are the two arguments related by phi prime. So the applications must be related by phi. Okay. Now the one-sided rules, which I think are the interesting part of our system. If you see I'm presenting the left one-sided rules, but you can also do the right rules. And the left-sided rules, so you see the term on the right is we have T2 and T2, and we don't really, it's the same in the premise and in the consequence of the rule. And the only term that changes is the term on the left. So in the top of the slide, we have the abstraction rule, where we introduce the lambda abstraction just on the left. And to change it up a bit, I will walk you through the application rule. So we have, again, two typing judgments going on the same time. We have an arrow type for T1 and whatever type for U2. And then we prove that the argument of the function has the type sigma 1, and then the application has the type, well, sorry, there's a typo, it should be tau1. And then U2 doesn't change at all. It has the same type in the premise and in the post. And then we have the logical content of the rule. So what we say is that T1 is a function that has a premise, a precondition phi prime. And then the post condition is that U2 is going to be related to the application of T1 to its argument by phi. And then we prove that the argument indeed satisfies this precondition, and then the application is going to satisfy the post condition. Right? And then we put, again, these two parts together, and we have the application rule. We have much more rules in the system that I don't have the time to present. So I'm just going to introduce what we call the subsumption rule, but it's the usual consequence rule, or it will also be very similar to the subtyping rule of refinement types. And the important part of this rule is that it allows us to prove this theorem, which is that HOL and RHOL are equivalent. Right, so this is great, this is fantastic, because it means that our system does not lose any kind of expressivity from HOL. It also gives us semantics for RHOL, the same semantics as HOL. And it additionally gives us all the properties that the terms have in HOL. So for instance, you would get subreduction for free and so on. Right, but this is the key result of our key meta theoretical result, because it means that we have not lost anything at all from HOL, but we can now do relational reasoning over it. And so we wanted to show also that our system was foundational, and the way we show it's foundational is first by the previous theorem, in the sense that it's as expressive as HOL, and also by embedding other domain-specific systems. So in the paper, we show the embedding of 3 systems. So the first of them is relational refinement types. The way you embed them is very intuitive. So you just, in some sense, separate the types from these, from the logical content of the types. Then we have another system, which is the dependency core calculus. So we show how to track dependency properties in RHOL to prove properties like non-interference. And we also prove an embedding from RHOL cost. So RHOL cost is a system to prove what to compare cost of 2 programs in a relational way. And so the great thing of embedding this into RHOL is that we can verify new examples, because these systems cannot deal with terms that have different types or terms that have widely different structures. And more importantly, in RHOL we can mix functional properties and sort of monadic properties. So for instance, one of the examples we prove on the paper is that insert sort on a sorted list is faster than insert sort on a non-sorted list. And this cannot be proven in real cost because, again, they cannot do, they cannot prove functional properties, just cost properties. And yeah, so one of our co-authors, Marco Gaguardi, is going to give a keynote in FSCD on Thursday. And if you're interested in this, he's probably going to speak in more detail. So now, what I want to conclude with and what I want you to take home from this is that relational type systems, relational refinement types, so they have very good properties, which mainly the main good property they have is that they have very good synchronous reasoning on two terms that have similar structures. But once you want to do one-sided reasoning, they fall short. And HOL is also a very expressive logic, but it fails to exploit these structural similarities. And what we've achieved is that we combine this, in some way, the best of these two systems in our HOL. So we have all the expressiveness of HOL. We have two-sided reasoning, as in refinement types, but we also have one-sided reasoning. And we do not lose anything at all because of the equivalence theorem. And we like to believe that this makes RHOL a good foundational system on which to build relational verification tools. And this is also part of our current/future work. So we're going to extend this with effects, because so far we just have pure lambda terms. And we are also thinking of a way in which we could implement this system to check these properties in a machine. And with this, I would like to conclude, and I will be happy to take questions.